For centuries, we have operated under an intuitive assumption about reality. Human beings are small, finite objects inside an infinitely large container called outer space. Modern quantum gravity, specifically through holographic models like the ADSCFT correspondence, inverts that topology completely. The math suggests space is not a physical container at all. It is a lower-dimensional boundary interface generated by a deeper, high-dimensional interior. In theoretical physics, we divide this system into two parts. The bulk is the unobservable interior, an infinite-dimensional space holding all possible quantum potential. The boundary is the flattened 3D projection that we actually perceive and experience as physical spacetime. To understand how a dense interior projects into a readable boundary, mathematicians use a tool from category theory called a functor. A functor is a rigorous mapping operation used to determine if two completely different systems share a similar underlying structural architecture. By applying a functor, we can test whether the stages of modern holographic physics and the narratives of ancient Gnostic cosmology are describing a single shared architectural blueprint. These ancient texts provide a structural topology of information processing that closely tracks the operations of our most advanced physics. Look at this structural map. We start at the unconditioned origin point. Ancient Gnostics called this the Pleroma, an undivided fullness of infinite potential. In theoretical physics, this maps to the ADS bulk, or infinite dimensional Hilbert space. Both describe a realm of raw data lacking spatial distance. A finite observer cannot process raw infinite data. Without a compression filter, the computational load is paralyzing. To solve this, the system introduces a transduction operator. In Gnosticism, this is the Demiurge, a blind structural principle that takes the unconditioned light and constructs a bounded copy. In quantum tensor networks, this is the Isometry Tensor, a mathematical funnel that compresses high-dimensional data into a manageable format. Next, the system must enforce strict physical rules. The Gnostic Archons represent boundary enforcement mechanisms that limit traversal. In relativity, these are the Spacetime Metric Tensors. These mathematical constraints enforce distance and the speed of light, ensuring the localized interface stays stable. The final output is the Kenoma, the manifest universe, which maps directly to the Conformal Field Theory Boundary. This is the projected physical material world. What we perceive as objective reality is a low-density 3D holographic desktop interface, rendering a highly compressed fraction of the infinite bulk. If this boundary logic is a universal structural invariant, software engineers can use the same blueprint to solve modern artificial intelligence bottlenecks. Specifically, it addresses a primary problem in knowledge retrieval known as graph context bloat. We can visualize this problem through the lens of our functor. This massive web is the AI's vector database, the bulk. This small rectangular box is the large language model's context window, the boundary. Standard retrieval methods flood the context window with topological noise, grabbing too much raw data and overwhelming the boundary. To solve this, developers are beginning to replicate the universe's exact dimensional reduction algorithm, compressing the bulk graph into the boundary without losing semantic meaning. Step 1. Establish a Markov blanket. This creates a dynamic subgraph boundary, isolating the nodes relevant to the user's query and shielding the working memory. Step 2. Apply a disentangler operator. We prune away cross-community links to decouple irrelevant relationships inside that blanket. Step 3. Use the isometry operator to physically coarse-grain the data. We contract tight microclusters into single, dense macronodes, retaining structural meaning while dropping token count. Step 4. Execute a holographic push-forward. The system serializes this compressed macrograph into a flattened prompt string that fits perfectly inside the LLM's context window. This boundary logic appears to be the invariant mathematical grammar of information processing itself. Whether you're a mystic conceptualizing the Pleroma, a physicist calculating quantum gravity, or an engineer building AGI, you are executing the exact same mathematical code.